Hey there, and welcome. Today we're going to talk about the world's secret glue. It's the set of invisible forces that holds literally everything together. I'm talking from a single drop of water all the way to the code of life itself, our DNA. So, yeah, let's get into it.
Have you ever really thought about it? What makes water beat up on a leaf? Or why does honey flow so slowly, while other liquids are, thin as water? It turns out it all comes down to these forces that are always at play, shaping the world we see and touch every single moment of every day.
So, let's peel back the curtain and look at this whole spectrum of stickiness. It's all about something called intermolecular forces. These are the attractions between different molecules, and they're responsible for, well, pretty much everything we're going to talk about today.
Okay, look at this. The scale here is just wild. Over on the far left, you've got covalent bonds. These are the super strong forces inside a molecule holding the atoms together. But that's not our focus. We're looking at everything to the right, the forces between molecules. You can see they're way, way weaker. But don't let those small numbers fool you. When you have billions and billions of them working together, they are incredibly powerful.
All right, let's start at the bottom of the ladder with London dispersion forces. Picture the electrons in a molecule just randomly sloshing over to one side for a split second. In that instant, that side becomes a little bit negative, and the other side becomes a little bit positive. This tiny temporary flicker of charge can then attract a neighbor. It's the weakest force, for sure, but it's everywhere. Every single molecule feels it. It's like a universal, fleeting static cling.
Okay, so London forces are temporary, right? But what if that charge separation was permanent? Well, that's what a dipole-dipole interaction is. We're talking about molecules that are naturally polar. They have a permanent positive end and a permanent negative end. So they basically act like a bunch of tiny little magnets, always trying to line up and stick to each other. It's a definite step up in strength from those fleeting London forces.
And that brings us to the big one, the absolute superstar of these forces, the hydrogen bond. Think of it as a special, supercharged version of a dipole-dipole force. It only happens when hydrogen is bonded to a really electronegative atom, which is just a fancy way of saying an atom that's super greedy for electrons, like oxygen or nitrogen. This setup creates an incredibly strong attraction that is absolutely fundamental to life as we know it.
And wow, does this hit home? Just let that sink in for a second. The literal blueprint for you, for me, for every living thing on this planet is held together by this one specific type of molecular attraction. It's the perfect strength, strong enough to keep our genetic code stable, but just weak enough that it can be unzipped when it's time for our cells to copy it. It's amazing.
And it's not random, not at all. This pairing is super specific. The rungs of the DNA ladder are formed because thymine only bonds with adenine, and cytosine only bonds with guanine. It's this beautiful, precise system held together perfectly by nothing more than hydrogen bonds.
Okay, so we've got the theory down. We know what these forces are. Now for the fun part. How do they actually build the world around us? How do these invisible pulls and tugs create the properties of things we can actually see and feel? Let's start with liquids.
You see, these forces are behind so many of the things we just take for granted about liquids. The stronger the forces between the molecules, the higher the surface tension. That's what makes water beat up into little domes. Stronger forces also give you more dramatic capillary action, which is how plants suck water up from their roots. And, of course, stronger forces create higher viscosity, which is just a measure of how much a liquid resists flowing.
A perfect example of this is glycerol. If you've ever handled it, you know exactly what I'm talking about. It's super thick, like syrup. That high viscosity is a direct result of the powerful hydrogen bonds happening between all those glycerol molecules. They're all clinging to each other really tightly, which makes it much harder for the liquid to flow, compared to something with weaker forces like gasoline.
All right, let's shift gears from liquids to solids. Now in solids, the arrangement of all the little pieces is everything. These forces don't just decide if something's going to be a solid, they dictate its fundamental architecture, creating everything from the jungled up chaos of glass to the perfect repeating patterns of a crystal.
So when it comes to solids, they basically fall into two big categories. On one side, you have crystalline solids. Think of salt or a diamond. Everything is in a highly regular, repeating structure. It's pure order. Then on the other side, you've got amorphous solids, like glass or plastic. Here, all the components are just kind of jumbled together with no real long-range order at all.
And for those super-organized crystalline solids, that perfect pattern has a name. It's called a lattice. You can think of it like a 3D blueprint, or maybe the scaffolding for a building.
It's this fundamental framework that gives crystals their distinct shapes and all their cool properties.
Okay, and this is where things get really cool. Because once you understand the blueprint, you can start messing with it. We can become these tiny molecular architects, mastering these forces to build a whole new world of materials with properties we designed.
A great example is making metal alloys. You can start with a basic metal lattice, like copper. Then you can make what's called a substitutional alloy, like brass, by just swapping out some of those copper atoms for zinc atoms, which are about the same size. Or you can create an interstitial alloy, like steel, by taking an iron lattice and literally stuffing tiny little carbon atoms into the gaps. That difference is what makes steel so much stronger than pure iron.
But it's not always about just mixing stuff together. Some of the most game-changing materials out there aren't mixtures at all, but these incredible continuous networks of atoms.
Let me introduce you to graphene. You know the graphite in a pencil? It's really just countless layers of carbon atoms stacked on top of each other. Well, graphene is what you get if you can manage to peel off one single one-atom-thick layer from that stack.
And this stuff, this one-atom-thick sheet, is basically a superhero material. It is ridiculously strong, but also incredibly light. It's almost completely transparent, and it's an amazing conductor of both heat and electricity. I mean, its discovery was so revolutionary, it literally won the Nobel Prize in Physics back in 2010.
And this idea, this ability to tweak things at the atomic level, it doesn't just give us super strong materials. It's actually the very foundation of our entire digital world, all thanks to semiconductors. See, pure silicon conducts electricity, but honestly, it's not great at it. To get the control we need, we use a process called doping, which just means we intentionally add tiny, precise impurities. If you add atoms that have more electrons in their outer shell, you create what's called an N-type semiconductor. If you add atoms with fewer electrons, you get a P-type. And that is the fundamental trick that allows us to precisely control the flow of electricity, making all of our computer chips and transistors possible.
So, when you step back and look at the big picture, from the biological code that makes you, held together by millions of tiny hydrogen bonds, to the silicon chips powering the phone you might even be watching this on, it's just incredible. Our entire world, from the life inside us to the tech all around us, is literally built on these tiny, invisible attractions. They really are the secret glue that shapes everything we know. And that just leaves you with this one kind of mind-blowing question. We've gone from just discovering these forces to actively using them to engineer our reality. So as our understanding gets even better, if we can truly precisely control these fundamental forces, what are our limits? Is there a limit at all?